Equivalent circuit means that we are replacing my existing device with a combination of elements to properly define that particular device. The elements which will be replacing the device are going to approximately give the characteristics of that particular device. This helps us in analysis of the device characteristics or its working in a particular set of circuits. So the first type of equivalent circuit for a diode is my piecewise linear equivalent circuit. So in this piecewise linear, what I am doing is I am approximating this knee voltage region with a straight line, with a linear region. So because of this linearity which we are assuming, this is why it is called, that is why it is called as piecewise linear. In this assumption, what I am doing is I am basically replacing the diode with a battery with a resistance, that is average resistance of that diode, and this becomes my ideal diode. So over here, the slope of this line, particular line, will give me the value of my average resistance. So the average value is basically the resistance which is present when the diode is in the on state. The ideal diode represents that it does not allow a reverse biasing to be present in the circuit. That is, it will allow only the current to flow in one direction only. The battery over here represents the junction voltage which is developed because of the depletion region. The battery actually indicates that if my voltage which is applied to this diode, it exceeds the value of this battery, then only the diode will be in my conduction mode, that is in the on state. In the reverse mode, this diode, because of this presence of the ideal diode, it will be working like an open circuit. So this is my piecewise linear equivalent circuit. Here you have to understand that my battery over here, that is Vk, is not a independent source. That means that if I apply a voltmeter across a isolated diode from the circuit, I would not be getting a value for, if I am considering a silicon diode, a 0.7 value across it. Next type of equivalent circuit is my simplified equivalent circuit. So in this, the simplification which is done is, instead of assuming that there is some average volt resistance which is present in the diode, I am assuming that when the diode enters the conduction mode, it does not have any resistance. Now this assumption can be done if my resistance which is present in the circuit, which is external circuit, external to the diode, is having a resistance which is much higher than the resistance which is provided by this diode. If in that case, I can assume that there is a zero average resistance which is in my diode. So if I want to replace my diode, I will be replacing it with a battery which is the same significant value of battery which is present in the diode in the earlier case, and a ideal diode. So this becomes my simplified equivalent circuit. The third and the final equivalent circuit which is present for diode is my ideal equivalent circuit. In this, I am assuming that my average resistance is 0, and also the Vk, that is a battery which was there because of the junction voltage, it is also 0. This approximation can be done if the voltages present in my external circuit are much higher than this voltages which is normally present across the diode. Now next topic is my transition and diffusion capacitance. Now in any electronic circuit or electrical circuit, if we consider any device, electronic device or electrical device, if we consider, it is basically a frequency dependent devices. That means they are frequency sensitive. That means for various ranges of frequencies, they will be having a different characteristics present in that device. Even if we consider the resistance of a normal resistor, it will also vary according to the frequency which is applied to that resistance. For the ranges of mid frequency to low frequency to mid frequency, the resistance value will be stationary or stagnant in nature. It will be having a fixed value. But as the frequency increases, because of the stray capacitance and stray inductance, it will have a increase in its impedance value. This hence increases the resistance which is offered by this resistor. If we consider diodes, the stray capacitance have a predominant effect rather than the stray inductance. Now let us see the different capacitance which are present in my diode. Now the presence of this capacitance, what happens is, for a low to mid frequency range, I can see that capacitance has a value, that is capacitive inductance has a value of 1 upon 2 pi fc. This is the opposition basically which the capacitance is going to provide to the signal which is passing through it. So if we assume that there is some capacitance present in my diode, its value is C farads, and the frequency which is applied to is F, then Xc is given by 1 upon 2 Fc. Now for a low frequency, this value will be almost tending to infinity. So since it is infinity, it can be assumed to be an open circuit. Normally this capacitance are present in a parallel fashion. So because of their open circuitness, they won't be affecting the diode's characteristic. But as the frequency increases, this value tends to be a lesser and lesser value. So the opposition to the signal will be reducing because of this. So this capacitance basically provides a low opposition path to the signal which is passing through the diode, and hence the characteristics of the diode changes because of it drastically. Let us see the two different types of capacitance which are present in my diode. To understand the first type of capacitance, we have to consider the reverse biasing mode. So I know that capacitance value, the basic standard formula for capacitance is given by epsilon A by D, where epsilon is the permittivity of the insulator, A is the area, cross-sectional area of the insulator material, and D is the distance between the two plates, conducting plates, which is across the insulator. Now in the reverse biasing mode, there is an increase in the depletion region. Depletion region does not have any free charges present. So it can be assumed that it is acting like an insulator. So because of the increase in the depletion region, that means that there is increase in my D. So because of this increase in my D, there will be a decrease in the capacitance. So because of this decrease in the capacitance, there will be certain effects which are present in my diode. This type of capacitance which is observed predominantly in my reverse biasing is called as my transition capacitance. The next type of capacitance is my diffusion capacitance. Now when we come into the forward biasing mode, we will be observing a minute fraction of transition capacitance, but the most predominant capacitance present in my forward biasing is the diffusion capacitance. Now this diffusion capacitance is nothing but it is because of the rate of charges which are injected into the region just outside the depletion region. Because of the increase in the charges in the forward biasing mode, the value of this capacitance also increases. These two capacitance are going to be basically going to help me to decide whether the diode is going to be applicable for a high speed diode or a low speed diode. These two properties are helpful in designing various other types of diodes depending on the application which it is being used. Like for my transition capacitance, there is a special type of diode which is going to vary the capacitance with respect to the voltage which is applied to it, which is observed in the transition capacitance. These capacitance can be denoted in the equivalent circuit in this manner.
Thank you for watching our videos. If you have any doubts, please do share in the comment section. For information on us, you can go and look it in the about page. It will also give you the schedule of the videos which will be coming up in the month. Do like and share and subscribe our channel. This will help us make more videos like this on different topics. Do watch videos on other topics also. Thank you and keep learning.